Hi! In the last couple of videos, I showed you a lab power supply build using old power bricks and a linear regulator output stage. It has generated quite a bit of interest. Now I have crammed everything into the case of a broken power supply. And by the way, the case belongs to a BK1696 power supply, which I did a couple of videos on a couple of years ago. And it had a bad LCD. If I manage to find a donor LCD, I will put everything back, as so far the changes I made here are fully reversible. But for now, I'm using it as the housing. Anyway, just wanted to power it up and give it a quick demo here. And I have it retrofitted with a voltage display here. So let's power it up. And I'm just going to quickly ramp it up. The first click you're going to hear is around 9-10 volts. And it's right here, and that switched the power supply configuration, if you remember. And the second one going to be clicking at around 20 volts. And here we go. So everything works just as designed. And now, of course, I have this case in, and I definitely can put this power supply into good use. Of course, if you don't mind the output stage being a switcher, which usually has worse ripple noise and worse voltage regulation compared to a linear one, then you have a lot more choices. For instance, you could get a DC to DC buck converter like this one for under $10. This one I bought from eBay, for example, is based on LM25116 chip, and this board is actually quite capable. It was claimed to be able to handle 300 watts, 20 amps output with a maximum input voltage of 40 volts. And based on my testing, it is really not that bad. With no forced cooling, I was able to run it at 24 volts and 12 amps for quite some time. The heatsinks were quite warm, but you can run it continuously at that level with a cooling fan for sure. And if you desolder these potentiometers for the current and voltage setting and replace them with ones, say 10-turn precision ones or just regular ones if you like to, you can definitely make it a nice power supply out of this DC to DC converter board. Of course, if you can afford spending a little bit more or simply just don't want to be bothered building or modifying the output regulator stage, you can get one of these Riden power supply modules. This one here was sent in by Banggood. It is a RD6012, which has an adjustable output up to 60 volts and 12 amps, which is plenty for lab use. It is the Wi-Fi version, which means it comes with Wi-Fi module. You can also buy an adapter that supports the RS485 protocol if you want to. I will leave a link in the video description down below if you want to get one of these RD6012s. And by the way, since there are 3 different versions, I wanted to show you some of the key differences you should be aware so that you can choose the right one for your own use. Here are the specs I printed out from the user manual. As you can see here, there are some key differences besides the maximum output current ratings between the 6 amps version and the 12 and 18 amps version. The first difference is the output current setting measurement resolution. And this is not surprising, as I would assume that the same ADC is used for all these different models. And if you increase the current range, you are going to lose some resolution. So that's why we have a 1 milliamp for the RD6006 and 10 milliamps resolution for the 12 amps and 18 amps version. The next difference is the output ripple. Again, it is not surprising to see higher ripple at higher output current, but I do wonder if the overall output ripple is worse for the 12 and 18 amp version. But curiously, for the 6 amp version, we do not see that the ripple was specified at a specific current setting. One thing a bit surprising is the automatic cutoff current values for charging. You can see that for the 6 amp version, the cutoff current is at 10 milliamps. Basically, the way this power supply charges is essentially current limited at a fixed voltage. As the battery voltage approaches the set voltage when getting charged, the charging current would drop. So for the 6 amp version, it considers the battery fully charged when the current drops below 10 milliamps. But For the 12 and 18 amp version, you see here it would cut off charging at 100 milliamps. This is fine for large batteries, but it would be unusable for charging smaller batteries like your rechargeable AA or AAA batteries, for example. I wish it would allow user to override this value, but I don't believe you can change the value specified here. If you intend to use this power supply to do a lot of battery charging, you may want to take this limitation into consideration. And the dimensions of these three different models are essentially the same except for the depth, so they should be able to fit in the same case. And just to put things into perspective, you can see that compared to the Array 3711A, the size of this power supply module is relatively small. And it's in fact just a little bit larger than my 2709B multimeter here. And from this page in the user menu, you can see that the three different versions of slightly different PCB layout. And the 6 amp version, which is on the top, has a very different PCB layout compared to the rest of the two. In fact, the 12 amp version and 18 amp version, they are largely the same except for a few key components like this larger toroid and the input connector here. But everything, and also of course the larger relay here for handling higher current. But everything else, if you look at the cap layouts and the key component layout here, the 12 amp version and 18 amp version, they're largely the same. And now let me flip it over and we can take a look at the component side here. Here is the backside of the module. It contains two stacked up PCB boards. They are bound together via these three binding posts that solder onto the second board here. So it is not very easy to service, as you have to take the whole board out of this case, which is already very tight, and then you have to desolder these three binding posts in order to be able to service the board underneath. I won't go into the details on the design here, as there has been quite a few videos by others on this power supply already. Basically, it has a STM micro on the bottom side of the stack of the two boards that controls various aspects of this power supply. The switching circuitry here is centered around this TL594C PWM controller chip. This RD series of power supply module also has a real-time clock, and it uses a 1220 3-volt coin cell to power the real-time clock, and that is not as popular as a 2032, but I managed to find one and pop it in there. Now onto this Wi-Fi module. And not sure if you can see here, but it actually doesn't really quite fit through this opening here. It overlaps ever so slightly, and I think they could have designed it to make it slightly narrower so that it would actually sit flush with the main board here. But you know, I saw some people actually filing down the one side, and this is extremely close to the traces, so I wouldn't do that. But even just hanging out here a little bit, it doesn't really affect the functionality. Instead of buying one of those switching power supplies for the RD6012, I thought I would again use some of the power bricks that I have lying around. By the way, if you add in a switching power supply, a case, the total cost would be well over $100 if you're using the RD606. And it will quickly reach beyond $200 if you're using the RD6012 or 6018, which is not exactly cheap. For this build, I happen to have these two HP inkjet printer power bricks. Each of them is rated for 32 volts 2.5 amp, but in my test, they can easily handle 32 volts 5 amps each, continuously without any issue whatsoever. Here are a couple of pictures of inside of this power brick, and I had gone ahead and removed the earth ground as I did in my previous videos with my other power bricks, so that I can connect these two in series. This way I would be able to generate the maximum specified 60 volts output from the Riden power supply module. And of course, one downside of using these two specific power bricks is that they are not powerful enough, and I'm only able to get the maximum 12 amps under 24 volts or so output, but which is far more adequate than what I usually need. So let me connect these power bricks together with the Riden module, and we'll give it a test. And now I have put these two power bricks in series and connected to the Riden RD6012 right here. And you can see that I used the original connectors here and with the original sockets. And on each of the output, I have a reverse protection diode so that in case the output is shorted, the power supply is going to be protected. Now I have hooked up the RD6012 to the electronic load, and also I attached the multimeter to the RD6012, measuring directly at the output binding post, so we can read the voltage right here, as the wires would have some voltage drop when the current is high. Now let me power it on. And as you can see, it powers up really quickly. And by the way, I have already changed a couple of settings. I disabled the annoying sound whenever you turn the dial that you hear the beeping sound. So I turned that off, and also I changed the display brightness to the maximum level. And it does look very sharp here. And as I mentioned earlier, given our power bricks setup, we should be able to output 12 amps at 24 volts. So let's give that a test. And right now I have set up the output. As you can see here, the voltage set at 24 volts and the current set at 12 amps maximum. And you can use this I set and the V set to change the settings very easily. So now let's turn on the output. As soon as I turn on output, you can see that we get the voltage reading, and also we have the reading on the electronic load here. So let's jump directly. Actually, let's turn on the load first, and we'll ramp up the current. So now we're drawing 3 amps, 4 amps, 5 amps, no problem whatsoever. 6 amps, 8 amps. And we should be able to hit 12 amps. And yep, no problem whatsoever. So as you can see that the output remains stable at 23.98, which means it has relatively good load regulation here. So let me turn it back down. No problem at all. And now let's take a look at how high we can set output to be. And our input voltage right now is displayed here as 63 volts. So there is going to be some voltage drop on this switching power supply module, but let's take a look at how high we can turn the settings here. And by the look of it, right now, even though we're set at 61 volts, but we're not able to reach that. So it does seem that probably the highest we can achieve on this power supply, at least this arrangement, is 58 volts. And in order to get even higher, I probably needed to put in, say, 67 volts or so, but that's the limits of those two power bricks here. So let's ramp up the current here. And by the way, this electronic load is only able to dissipate 300 watts, so I probably won't be able to put it higher than 4 amps. Maybe we can do 4.5 amps. And you can see the output already dropped. It's 56 volts now, which means that it does require at least 4 or 5 volts between input and output. So let me actually lower the output to 56 volts, and now we may have regulation here. So let's change the current to 4.6 amps, and that's the fan from the electronic load as it is approaching its maximum load here. And we can see we can so we can achieve the 5 amps at the 56 volts range. Actually, that's not all that bad at all. So let's turn the load off. So now we kind of know the full range of this power supply. By the way, this power supply has a fan, and it occasionally turns on and off. Right now, I think it's on. Let's just see if it is on. Nope, it's off. And apparently everything is still very cool, so it doesn't need the fan to be on. But even if the fan is on, it's actually still pretty quiet. So now let's turn off this electronic load, as it's quite annoying right now. What I want to do next is to test out its charging capability, and for that I'm going to use this battery pack, and it's a lithium-ion battery pack, and I have 6 in parallel, so I should be able to charge it at a maximum of say 4.2 volts at 2 amps. So let's set it up here, and let's do voltage 4.2 and current 2 amps. So that, and for that I have to change this lead to the battery charging terminal. By the way, for most of the power supplies, the green terminal in the middle is a de facto, right, case chassis ground, whereas for this one, that's a battery charging terminal, so that is something different. Basically, this one does not have a earth ground connection here. And okay, so let's move on to the battery. For that, I'm going to hook up the battery here. I'm going to put it on top here so that you can see. And now let me enable the output. Not sure if you heard that, but that's the clicking of that relay. So clearly that relay is only used when you are doing the battery charging here, and which is very interesting. If you look at the diagram, I mean the pictures we showed earlier of these three power supplies, they each have a pretty beefy relay, and the 06 has the smallest one, and the 18 amp version has the largest one. Now that relay, the only functionality, the only thing it does really is to control this charging terminal. To me, that's a little bit wasteful, as most people using this power supply probably are not going to be charging batteries all day. And if you're just using the power supply itself, this relay does nothing. So not entirely sure why they designed it with a relay to control the output. Can't they just do that with a regular, say, MOSFET? I don't know. I'm not sure why they chose to do it this way. And as I mentioned earlier, this charging really is just a fixed voltage, current limited charging. So it doesn't have any smart built into that. So basically the idea here is once it approaches 4.2 volts, the output current is going to drop. And in this case, it's going to be, when it's under 100 milliamp, it's going to cut out. So for example, if I, let's take off this lead here. And you heard the relay clicking. So basically now, because it did not detect the current, so after a couple of seconds, basically it disconnected the circuit. So that charging circuit works, as expected. There's nothing special to that. Now I wish Riden would open source its firmware, as there's a lot of potential here. For instance, the battery charging functionality you just saw is really limited. But through firmware update, you can easily make it to be able to accommodate more sophisticated charging schemes. And the UI is also quite busy, in my opinion. For instance, there's no reason why would you want to show the battery charging information in a normal setting. And I wish it offers a bit more configurability so end user can decide what information to show and hide on the main menu. Another disappointment is the Wi-Fi functionality still has a lot of rough edges. As I found out, it appears that the Wi-Fi implementation is limited to 2.4 GHz band only, which means I have to switch from my usual 5 GHz bands to 2.4 GHz bands in order to use the Wi-Fi feature. Also, the app is rather intrusive. It requires location information and requires access to your photos and documents, which I don't understand why. If you don't consent to turning on the location, you won't even be able to connect via the Android app. So to me, if you are really serious about using remote controlling capability, connecting via USB is probably a better way to go, as the desktop app is far more feature-rich anyway. And I hope the USB is fully isolated, although I could not find any information in the user's manual on this. Connecting to the computer via wireless is still experimental and still does not work in the desktop version I downloaded. I suspect that the reason they are having a hard time implementing wireless is that they're not running any operating systems on the firmware, and so that they have to implement the entire hardware stack, which is typically abstracted away in the OS kernel and the kernel driver layer. And I thought I would spend a little bit of time showing you how to set the voltages and store them into the different memory locations and retrieve them later. The manual is a little bit of confusing, and in fact a lot of people doing the review that I watched, I haven't really seen them clearly demonstrating that, so I will give it a go and show you guys how that works. So right now I have already stored a couple of settings here. For example, if you want to recall, you press shift and memory 1, and it asks you for, right now I'm setting at 3.3 volts, and the second location I'm setting, I think I set it at 5 volts, 1 amp, yep, so that's 5 volts. So you can do that. For example, now we wanted to set, say, 6 volts output and a maximum 2 amps. We want to set it to location number 3. So what we do is we simply come here, we do a VSet, 6 volts. Of course, you can use a rotary encoder as well, and you do iSet, let's say 2 amps. And let's do the over voltage setting as well. So let's do 6.2, and over current, let's do 2.5. Let's say we're satisfied with this arrangement and we want to store it. So all we do is press mem and press 3. So it will ask you whether or not you want to set it as a third location. So now we stored it. So to test that, let's put something other than 6 volts in. Let's just say we put 617 here. And to recall the third location, let's do shift, memory 3. And you can see that we press enter. All we entered before now has been successfully recalled. Now, there's some confusion on one of the settings, several settings, in fact, on the menu side. So I'll try to explain that to you here. So for instance, if you come to the menu section here, it has a take OK. What the heck does that mean? Well, the take OK really means whether or not you want to confirm OK when you switch different ranges. So for instance, right now, every time we switch to a different memory locations, we were shown we're showing a dialog box asking whether or not you want to proceed. So if we turn it off, let's just do that. To do that, I can turn it off. And now I can go back to the main menu here. So this is not very intuitive how they let you navigate around the menu system, but that's a different story. Now, okay, so now remember when beforehand we switched different memory locations, we were prompt for confirmation here. So now if I do a M2, you see that it immediately changes to that 5 volts 1 amp, and here is a 6 volt 2 amps. So that's that memory, sorry, what was that? That's take OK, right? So the next one, take out, really is, I don't know how they come up with this English name, but it really means whether or not the output should be on. So by default, the output is off whenever we switch different ranges. And if you put the takeout to be true, so let's do that. And again, the operation could be thought out a little bit better, but that's not the concentration here. So let's do this, right? So now it's enabled, and we go back to our look how for the on off. So let's switch to, let's say, the first memory location, 3.3 volts at 1 amp, and it's on. And let's do the second, it's on. So now I noticed that there may be a bug in this specific functionality. As certain ranges I switch, now I can't reproduce it, but this actually turned off. But in general though, this is very dangerous. You don't want to do that. You do want to make sure that you confirm, and so is the different range setting. Range changing. So the default out of the box is actually the preferred way, and that gives you some confirmation in case you mistakenly pressed certain buttons. So now I'm going to change it back. So for the oops, see, it's not very intuitive, and I really meant to change this to take OK to yes and take out to no. So that's your default setting. And all in all, I'm pretty satisfied with my setup here with these two power bricks and this Riden RD6012. Again, I hope you enjoyed the video and learned something new. If you liked the video, please remember to subscribe, share, like, and I will catch up with you next time.